platform Dialogues, sponsored by or coordinated by the UNStudio Knowledge Platforms. Myself, Rob Henderson, Knowledge Platform Coordinator. Filippo Lodi is the Inventive Materials Platform Leader. Nuno Almeida, our Associate Director in charge of research, representing UNStudio. You may have seen today or this week website update. So the beginning of a kind of phase launch of the knowledge platforms, and as Ben is calling it, going open source, going online. It's about the restructuring not only of our office, but also of the interior of the office, but also the way that we work with all of our friends and partners around the world. So what we will focus on today, and with Filippo here from the Inventive Materials Platform, and also as the platform of the Salone, is materials. So we've asked all of you to speak a bit how you research into materials and how you deal with sustainability. Thus the name of the dialogue being Material Attainability. So I'll introduce briefly who will be speaking. First we have Micol Costi, who is the Director of Materials Research at Material Connections, Italia. Material Connections is an international group now, libraries around the world, I guess, and an online library, which we also participate in. James O'Callaghan, Director of Eckersley O'Callaghan, structural engineer specializing in glass, and we'll be talking about the advancements in glass that you're currently working on, research, new projects, etc. Michele De La Rosa, project manager from Permasteelisa, who, well, I won't give away what you might be talking about, leave it as a secret, but he's working on project manager around the world, based here in Italy, yeah? And Luca Achilli from Interface Flooring. Let's talk about life cycle assessment systems and a kind of sustainable strategy, sustainable and social strategy for material production. Sustainable carpets. And Giammichele Melis from Buro, Happold, London, who will take a couple of projects from opposite ends of the scalar and financial spectrum and talk about how material research plays into that. And last but not least, Gabi Böhm from Premier Composites in Dubai, who will be speaking about advanced composite building envelopes and how that from a small module into a large module becomes a composite facade. So, without further ado, and I didn't follow my slides. Basically the 4 knowledge platforms, and we find ourselves here today with the Inventive Material Platform and Micol Costi.
Is this work? Can you hear me? Can we maybe... I don't think they really can hear me too well. Now you can? Okay, wonderful. I'm lost without a microphone, as you can imagine. So, okay. Thanks a lot for passing by. There is so much to see around, so it's glad to see that someone still takes time to step by and take a look at the things we prepared together today. Our theme today is material attainability, which I think is a very interesting term to use, attainability. In fact, whatever your idea is for a project, sooner or later during development, you will have to find the best material solution for that. Best material solution has obviously a lot of factors to be considered because you have technical requirements. You have to make sure that maybe certain aesthetical qualities also will be satisfying. Then there are, well, the performances that these solutions have to have, the way you can deal with these materials, transform them, and obviously the environmental impact. Thank you. The environmental impact is also very important. Last but not least, the overall application potential of a material is something that the architect, the designer, can in sometimes less, sometimes more, in many ways contribute to develop and expand. So again, thinking of the term attainable, I took a look at some synonyms, and I just picked a couple of them. And the most important ones are obviously related to the fact that something has to be realizable, achievable, obtainable, etc. Then we have obviously then also conveniency, accessibility, etc. Feasibility is not to be forget, and ready for useness. No problem is also a term that I particularly like. And I just picked a couple of examples of possible material solutions which are quite versatile. So, for example, here we have a composite material. The main material is cement, but in fact the interesting thing is that it is consisting of a textile product as well. So actually the outer skin of the material is consisting of a neat textile, so it's fibers. Then the core material itself is a metric consisting of specifically formulated concrete mix, and the backing is a simple PVC backing. This is what the material looks like once hardened, and it's fascinating that on the one hand you see the outer face looks like a textile, but the consistency is that of cement. So the material comes rolled. You can use it in a very similar way as you would do with a textile product. You can even drape it. It's super flexible, and at the end, once hardened, though, it has the same characteristics as cement. Look at that picture. So you can very easily impart three-dimensional shapes, and then obviously paint the material, use it as you like. I don't need to explain much about cement, obviously, so it's extremely resistant. And through this solution, you may actually use it in the same way you would apply a textile. You can create drapings, for example. Here we have a funny project by a designer. What you buy is the frame in your favorite color. Then the textile comes rolled, and you can shape the chair in the way you like. And so we are taking a look at quite simple products, for example, chairs. But what is interesting is that since the material can so much be customized to the shape you want, and actually we were having a quick chat before starting the official conversation, and the term customization popped up quite a couple of times. So customization on a smaller scale and on a super wide scale is always quite significant. So here you can see how fast you can use this material, and leaving behind product design, more product design related projects, and thinking of architecture, we can see, like for example, a pavilion like the one you see can be prepared in a very fast way. So what you do is you have the delivery, the material comes folded, then all you need to do is inflate it in order to impart the final shape. Inflating is quite a smart way of using a super lightweight material, which is obviously air, in order to impart specific forms. Then all you need to do is hydrate the material, the typical just add water formula. So in fact you do just add water, and in the end, all you need to do is wait for the material to harden, which means that in a very quick and fast time lapse, you have a pavilion which is ready to use and operate within. Typically, if you think of maybe the need of organizing a hospital in a quick way, this ends up to be a great solution. Also, if needed, the structure inside may be sterile. As you can see, the structure then has total resistance against outer agents, UV rays, snow, etc. And maybe the picture is a bad quality, but you see there is someone stepping on the roof. So in fact, it is a structure which is ready to use and definitely safe. Another way of thinking of shaping things in a fast way without the need of it's not really without the need of molds, but the typical molds, as we think about a mold, it's always something rigid. Here it is something flexible, and what we have is a composite material which is fully bio-based. It has very recently been developed, so it's quite still waiting to get well known and be used. But the important thing and also interesting thing is that you can pick from a very large number of different natural fibers, and then these are being binded with a natural-based binder, which means that the final material is bio-based, and that means it is biodegradable. And you can add pigments as you like it and pick between 40 different binder types, which means under a technical point of view, you can pick the best solution for your project. You pick the fibers you want, and you can impart shapes. Here we see again smaller shapes, and this patented process, which is very low cost, enables you to create these shapes the way you want it by picking the beloved version of this bio-based material. This is what then the end product may look like. And again, we start from product design, smaller scale projects, but we can think of more. And here we can see that technically the way this works is you have an inflatable inner form, and this form you can shape as you want. So all you need is then pressure and covering this inflated shape, this balloon with a vacuum film. Then you spray on this bio-based organic material on this film, and this is a process which does not require that much energy consumption. Then obviously you have already picked the best version of this material. Then what you do is once you have sprayed on the material in the desired thickness, you cover it up with a further vacuum film, and then all you need to do is hermetically seal and wait for the material to harden. Then through compression and hardening, what you get is a material that in the desired formulation can also be class A or B for fire rating, and may be used for larger projects. So here is one of the first attempts for using this type of material for a carport, for example. Could be a temporary pavilion. We are in the design week now. Think of all the temporary structures that you can find anywhere in the city. So this is fully biodegradable, it's lightweight, and also it has very good thermal insulation properties. We are actually just here for a quick chat, so I just left out all the technical information in detail, but this is just to show how interesting developments may lead to many different applications for materials, and also it is nice to see how new solutions really have such a great application potential. Same here, this is a wood processing technology which has been developed with the aim of seeking for an alternative to traditional woodworking techniques. and the objective was making wood flexible, highly flexible, and here you can see how you could be able to use and bend this material. It is highly resistant, and it may be used if required together with acoustically insulating fabric, which is very thin. So this is what the material looks like and what it can do as well. You can use it, you see it has a behavior that is rather to be compared with the behavior of an elastic flexible textile. You can even knot it if you wish. This is you can see the difference. The picture up left is the regular version. Down on the left, you can see that this acoustically insulating textile has been added. Same textile in green on the right top. And so you can create structures which are highly versatile, very easy to move and shape, and eventually also replace, which are highly acoustically insulating. These are acoustic panels. And here, as a quick hint of what the material may do for an architectural structure. So this is also quite new, not yet well known, and still seeking for interesting projects to be picked for. So we can see that highly flexible structures may be created with this type of material. And as a final example, when we think of flexibility from material, what we also may appreciate is the fact that the material is flexible and actually has an active behavior. And it is the case of this thermodynamic glazing. So this is a composite panel, which is interesting because the outer layer is a prismatic material, which is able to reflect light. Then we have an inner core made of phase change material, which means that depending on the weather conditions and on the season, the material automatically insulates the interior of the building in the best way. Here we see the phase change material has a transition from its liquid state to the crystalline state, and this phase change core is guaranteed for 100 years. So if you're wondering if this actually has a certain lifespan after which it does not work that well, it seems that it does. So here we have, some technical data we will not look at too closely, but what is interesting is that by using this material, you have natural light you can benefit from, and at the same time you prevent the buildings from overheating inside during the warm seasons, and also from being too cold and requiring energy consumption for air regulation when it's cold outside. In fact, I just said it was just a couple of examples. I hope they were interesting, and I'm very curious to see who's the next speaker. Am I passing on?
James.
James.
So,
okay.
yeah, from
so the next one is James.
Flexible glass to
flexible glass.
Flexible glass, yeah.
I'm going to stand over here because I couldn't see the screen. So, that's not my slide. Sorry. Okay. So I'm going to talk briefly today about glass in a couple of different forms, in its more traditional, recognized form, and also about a material that I've been working with for the last couple of years, which is follows on a little bit from this flexibility idea and new composites. We're a structural engineering firm. I've been working in the field of glass design for the last 10, 15 years, and these pictures are terribly small. I didn't realize the screen would be this small, but it's just a sample of some of the projects we've worked on. We've had the good fortune to be working with Happold over the last 10 years in their retail expansion around the world, and a very big part of that has been their interest in exploring ways in which glass is used as internal structures, and as a result of that, we've benefited from their interest in the research and development, which has been quite interesting in how we can push glass fabrication, glass techniques and connections forward. So lots of staircases and buildings and things like that, all of which have had a incremental step in technology and innovation. Some of which, if you've been to New York or wherever around the world, you may recognize. So glass itself is essentially, in its raw state, a planar material. So in order to create something that's three-dimensional, it needs to be connected. So therein comes the challenge. Once we connect it together, we have to introduce something that are connectors, and those inevitably tend to be opaque. And the more connectors we have, the more you see. It's transparent, so it's the connection. So often, as I say, in designing glass, it's not about the glass we're designing, it's about the connections that join it together that is our focus. So, if we're able to do something to focus on those connections and make them as sleek and as transparent or as minimal as possible, that's important. Or if together, to reduce them in number. So one way of doing that, first idea was the way we explored connections themselves. Traditionally, glass has been connected by gripping it, by bolting it, by putting holes in it. And over time, we started to look at ideas about 10 years ago now, where we started to look at ways in which we could laminate things within the glass itself, so stripping away a layer of connection, so enabling us to connect directly into glass panels in order to take quite high structural loads. So again, this is all based on my background, which is making glass work as a structure rather than perhaps making glass work as a facade, where the loads are not necessarily quite so significant. So this some very early experimentation, and we started to come up with some rather neat ideas about how we can start to put things into the body of the glass, and then preserving the surface of the glass, having that reflective surface of the glass in all faces. So this is an exploded view of that, of a connection which we then developed. This is in fact in its manifested state of in a project in New York, where in fact everything you see in that connection is inside the glass, and it's a full mechanical connection carrying quite significant loads between fins and glass. So no bolts, no connections, and that sort of thing. The other thing, moving quickly on in order to keep to our little time frame here, another way of reducing connections is to make things much bigger. So by making it much bigger, we need less connections and less pieces. So this is a sort of dual track of research that we've been carried on, and that involves laminating glass in very, very big autoclaves. This is in fact an autoclave in Germany, which we, just to give you a perspective of size, which is just coming online, which is now 18 meters by 4 meters, enabling us to make panels of glass that are now 15 meters tall by 3 meters in single pieces. This is in fact in China for a project that we did in Shanghai. As you can see here, there's now this cylinder is 13 meters tall, 10 meters in diameter, and has no horizontal joints. So there's no break in that glass over its full height. It's obviously joined at its vertical seams, but of course, this particular image gives you a much better idea how you can therefore get more transparency. There's, of course, the connections are there. They're still inevitable. We haven't got to the point where they don't exist, but by integrating them into the glass and reducing them in number, you can get this much more transparent. Perhaps the best example of this was this project in New York. It's a very famous project on Fifth Avenue for a glass cube for Apple. This was built in 2006 using 90 panels of glass and as many a number of different fins that joined it together. By using the same, by embracing some of that fabrication technology we'd pushed through in terms of larger format glass and also in terms of connections, we took that 90 piece of glass structure down to just 15. So you can see that there's clearly that many less connections, that much more. So you go from something like this, which is of course in itself quite beautiful, but has a density to it, to something like that, which is significantly less dense, which is what's there today. So we had so this is the rebuilt version of the same thing. Moving quickly on to a material in particular that I've been working with over the last couple of years for a company called Corning a glass company in upstate New York who've done an awful lot of research. In fact, they are primarily a research company into ceramics and glass. They came up with this product called Gorilla Glass, which is actually a byproduct of something they came up with a long time ago in the 1960s, which is fusion glass. And it has particularly unique properties in that it's particularly strong and it's very flexible and very thin. So what's fusion glass? This is just a little bit of timeline about where this came in, but you'll see, in fact, fusion glass was something they developed in 1964, and it's a product they've only started to bring off the shelf into commercial use in 2007. And what precipitated that was, in fact, the mobile phones, iPads, LCD screens, where this glass is, in fact, used as the front of your phones and your devices. It's a very thin, very, very strong glass. How is it made? It's made in a very different way from normal glass. Normal glass is floated out on a bed of tin on a float line, whereas fusion glass is in fact formed in a vat about that high up in the air, and the glass flows vertically down without touching tin or touching any impurities. And by doing that, it fuses in itself as it drops through air and cools. I won't go through this little video which explains it. I think that's going to work, is it? No. Okay. And as it collects, it's then sliced as it drops through, but it's very thin. In fact, it's so thin you can, in fact, now roll it up and then roll it into a big roll, like a piece of paper. But once they take this fusion glass, they then, with the particular product, Gorilla Glass, they take that glass and then they put it into a chemical bath and chemically temper it, which is an ion exchange process, which allows the ions in the surface of the glass, which are sodium ions, to replace with potassium ions in the salts. The potassium ions are much fatter, so they have to crunch together on the surface of the glass, and that crunching together gives the surface of the glass a very high compression, and that high compression gives it the much higher strength it otherwise would have. So you end up with a very thin, super thin, 1 millimeter and less, very high strength, 300 megapascals piece of glass. So a 1 millimeter piece of a Gorilla Glass, like your screen on your iPad or your iPhone, has a strength that is many multiple times greater than that of regular glass, and in fact a multiple times greater than that of steel. So here we have very thin, very strong glass, very durable. What do we do with it? So what we've been looking at is ways in which it might be useful to use that in the world of architecture. And we're going to show you some examples of what we found from that. So we thought about it a little bit. We thought about what could you do with it? Well, what do you do with really, really thin glass in a building? Buildings need typically much larger apertures. Very thin glass is going to be very flexible. What might you do with it? So you might combine it with other materials. So in fact, by combining it with regular glass as a laminate, or even combining it with plastics in particular, you can create composites of glass and plastic with a glass surface, which then become much, much lighter than glass, which you can then use on roofs or in any places where, in fact, lightness becomes important. You might also think about it in security and in bomb glass, etc., because it has much, much higher strength. It's much thinner, so it can absorb much higher stresses and the like. And the other thing was, of course, how might you use it in a building? How might you embrace that flexibility to create surfaces on a building and perhaps address some of the trends of architecture today, where things are becoming more complex in their geometry due to the nature and tools that we have at our hands to be able to make that happen. We did a series of tests. This is all a little technical, I guess, but essentially probably the most important thing to note is that with a regular piece of glass, when the glass breaks, it loses its strength because of the lower piece of glass breaks in a laminate. With a Gorilla Glass, what we found is that by failing the middle piece of glass, by sandwiching it between two very thin pieces of glass, we broke the middle piece, but in fact, the containment of the very, very high strength skin on either side of this regular piece of glass enabled it to continue to carry load to 4 times, 5 times its breakage load. So it has a very, very high post-breakage behavior, which then sort of leads you to the idea that, well, that's interesting. Where do you need something that has a very, very high post-breakage behavior? Well, it tends to be in something that has a very, needs to perform in a very unique action, like a bomb or a security issue like that. we looked at, so we're sort of starting to head down the road of things that need this sort of particular post-breakage strength, and also things that might need this lightness, light touch, light materials, lightweight glass, as I like to call it. So for all intents and purposes, you're looking at it and you're feeling a piece of glass, but in fact its central body is that of an acrylic. You get away from the greenness that's in the glass because the acrylic is completely clear. So you then have you can have a 15, 20 millimeter piece of glass that has no greenness to it whatsoever. So this is just a little bit more about the fail-safe and how we then looked at it in terms of how it performs against regular panels, against its strength and its stiffness. It's not that dissimilar to that, so you're not looking at its much benefit in terms of that. You're looking at how it combines in color and some of the other things we looked at. Blast resistance, we found that to get the equivalent piece of glass doing the same level of blast, if we take you'd be looking at sort of 4 layers of regular glass against 2 layers of regular glass with a Gorilla Glass core. So you could end up with much thinner bomb-resistant glass or much thinner blast-resistant glass than you might traditionally otherwise had. Or with traditionally where it's combined with acrylics, that you get problems with scratch surfaces and things like that. So that's where that comes to. Flexibility, well, we've got lots of buildings these days with lots of flexible surfaces. The great thing about this glass is you can bend it and cold bend it to very, very tight radiuses and form it into very different sinuous shapes. So we're starting to look at examples and trying to find examples where it might be useful to use glass in a way, perhaps on a surface of buildings or inside of buildings, where those curves, which are very traditionally very difficult to achieve with glass, might be more easily achieved with this very strong and flexible material. Great examples are ETFE foil, where that's been used on buildings. We're now in a position where we can replicate that kind of geometry and that kind of curvature with the glass itself, without the sort of downsides that we have with ETFE and composites and things like that at a similar weight. Similarly, tensile structures always have been of a fabric. With the glass is so thin, it's more like a fabric than it is in its physical stiffness is more like a fabric, and its strength is super high tensile strength, so we can put it into very, very high tension. We can form it in different forms. How can we then embrace that and create fabric type structures out of glass, transparent fabric structures out of glass? These are some examples that we were doing for a project in London, where we were starting to take very tight curves, very sinuous curves, and creating it in another form, in a tower we're looking at, where we're actually creating various different, embracing the curvature of the glass, not only visually, but also to create stiffness of it. And that's where we're sort of at right now.
Thanks, James. Michele.
I will. Can you hear me? Yeah. Just a brief introduction of Permasteelisa, a group of company, and then I will go faster in order to discuss about the 2 research projects that I will introduce today. Permasteelisa is a group of company that work basically in building envelope and have a worldwide leader in contract Turkey project. So we basically follow all the activity in a project from the design, engineering, so project management, manufacturing and installation. We started in building envelopes, but we move also to interior system projects in order to cover all the building furniture at least. We have all over the world offices and factory in order to be able to build the building. I mean, in quickly, because we build quite big building. So we must be very flexible and ready every day for the market. We are organized in 3 main divisions. As I told you before, exteriors, because Permasteelisa about 40 years ago started the activity just building exteriors. But in the last 20 years, we move to interiors and also contract that cover all the Turkey project, and we should realize from public or residential building, but also special applications such as hospital or so bridge covered by glass. I mean, our ability is to try to realize what the architect would like to build. Permasteelisa, as I told you, is a group of company. The 3 main brands are Garner, that is based in Germany, Skeldebat, that is based in the Netherlands, and as I told you, Permasteelisa, that is Italian, and in Vittorio Veneto. Okay, here you can just see how we are organized. We have about 16 design office and 11 production plan, or better, some of the production plan are fixed, and 4 of them are called movable factories. So we must be ready to build where we have to build the building or the construction. So present in 4 continents, but also in Africa we did something. As I told you, we are leader in the construction of building with high requests that arrive from the architect. I mean, we used to work with all the main name from Gary, from Foster, UNStudio, obviously, that I didn't follow the project with them, but I appreciate a lot of the work that have been done together. So as I told you, after this very brief presentation of Permasteelisa, I spoke about 2 research project application that we are developing right now in Permasteelisa. And the 2 examples are the related one to innovative material develop, and another one is innovation system for using existing material. I mean, sometimes is just the way to use existing material and the ability to do that is a request for the architecture. But sometimes also architects ask us to invent something new. Okay. In the last 5-10 years, as all of you know, is very important. Not just to build something with a very beautiful shape or building that could be functional or whatever. But the sustainability solution for the environmental became every day the most important way to build a building. All of you knows all the target that we have, the 20% energy produced itself by the building, or the direction that we are going to, that is nearly zero building energy consumption. And so we have to integrate material technology in the building in order to reach this target. Okay, so I will go directly to the two projects, the research project that I will discuss today. The one relevant to material already existing, that is this tech facade that is made with fiberglass. I just show you a couple of images and then come back to the explanation of this technology. This is the internal view during day and the external view during night. As you can see from this picture, just using another material instead of the classical aluminium in all the components, we have built this facade that have very high performance, very high energy performance in order to reach the target required by developer, architect, and so back to that, we also the occupant comfort, as you can see from the previous picture, is every day a target required by the architect, because it's need for the occupants that live in the building. All the components of this facade are fiberglass, except obviously the glass. And so also the life cycle of this product is think about to reduce the energy consumption of the global life of the material. Instead of using materials such as aluminium, we move to this technology. It's still a mock-up. We did not realize yet one project of fiberglass, but in any case, the performance mock-up have been I've done a few months ago, and so we are ready for the market with this technology. Another project that Permasteelisa is working on is a new material. What I presented before, as I told you, is just application of existing material. But we would like to go ahead, try to still be the leader. So we will think about to invent a new material for building application. Permasteelisa, together with ERG and Free University in Italia, have in the last 4 years done a lot of research in the organic photovoltaic, also called dye solar cell. Also, in this case, better to see before the picture and then back to the technology. As you can see here, this photovoltaic is semi-transparent. the standard photovoltaic is obviously not transparent. You can see all over application of photovoltaic, but unfortunately, if we add some photovoltaic on glass on spot, could be semi-transparent. But in this case, the concept is different. I mean, the red one, as you can see in the glass, is the organic photovoltaic. The technology is quite easy. In between two glass, you put some material such as titanium dioxide, color, and then you close two glasses, putting inside electrolyte. And the technology is the printing, the screen printing, so quite easy technology. And what you obtain is a material that looks like that. If we have to go to nearly zero building, that is the target in at least 10 years, we hope, we have to try to produce energy not just at the top of the building in the roof or in the spandrel area that usually or could be used for photovoltaic, but also we have probably to move to the vertical facade in order to have the feedback of try to reach the 100% energy consumption with some material that it is active. Okay. Obviously, the problem, and today could be an opportunity also maybe after the presentation to share ideas, is how to apply in a building such material. We have tried to do some research, and maybe some element could be used for application. Vision part probably is a target of the future, because we should move to different color, but obviously to have a glass active, it must be colored. But probably one way is to leave just one part of the vision part with clean glass, and all the other possibility is to use that kind of glass. The good here, the target are obviously to have a lot of color, move to uniformity, but the good target is to turn the transparency, and so maybe some application the transparency could be lesser, in some application the transparency could be higher, and try to mix all the opportunity that this product have. Probably should be one way to have some active element in the building. So this is, and obviously scaling up, because now it's still a research project. We had some very good result, but we need some time to be ready for the first application. But probably in few years, in a couple of years, some element could be big enough to be installed in a building. Okay, this is.
Thanks, Michele. On to Luca. Yeah.
Oh, where's best to stand, I think? There? Yeah. I shall stand here. Okay. Okay, so my name is Luca Chili. I work for Interface. I work for the Innovations Department. And who we are, Interface is a multinational, it's a global company that makes carpet tiles. And you know, you'd think carpet is a very simple thing to manufacture, something low-tech, but it really isn't the case. We are a $1 billion company. We have 3,500 employees globally, and we have 6 manufacturing plants. We have in the States, in Europe, Thailand, China, and Australia. And we are a company that is driven by sustainability and a sustainable product. Our founder sadly died a couple of years ago, Ray Anderson. He in 1994, he had an awakening about the product that he was making. He was making carpet tiles. He was making a product that was 100% oil, refined oil of some description, and the sustainability of the product was just awful. Excuse me, was just awful. So in 1994, he said, you know, one day people like me are going to go to jail because you know it's just. It wasn't the way to go, and so he decided to embark upon the sustainability journey, and he came up with his Mission Zero, and which is our really our mandate, and is to be in a position in 2020 where our company is going to have a negative or neutral impact on the environment. So our products are going to be completely carbon neutral. And it is a very ambitious project. We were the first in the industry to embark upon this very, very ambitious mission. But that's what really made us become leaders in the market and really the ones to follow. So the tough questions of our Mission Zero are, can we eliminate our impact while delivering more to our customers? Can a petrochemical company, which is effectively we are, aim for zero impact products? Can a company do well and do good at the same time? Because it's not just about ecological sustainability, we're also looking at social sustainability, which is as important, we believe. So if you look at a breakdown of, and we have, of our product, you can see the life cycle assessment, what it is. I don't know if you are aware of the term. It's basically you really put a number as to what the environmental impact of a product is. And if you look carefully, you can see on the left-hand side that the biggest contributor to our to the impact of our product is the raw materials that make up our product. The manufacturing is just 9%, transportation, upkeep and end of life are smaller contributors to the life cycle assessment. So if you look at this, we want to make our products more sustainable. So if you dissect that raw material contribution to the life cycle analysis of the product, you see that the yarn, which is the part of the carpet on which you walk on, usually made of polyamide or nylon, is about 45% of the whole product. So if you factor in a number of things, 50% of the total environmental impact is can be attributed to the face yarn. So although we're looking at decreasing and improving the impact of the other components of the carpet tile, today I would like to talk about the yarn. So how can we reduce the impact of the yarn? Because if we do reduce the impact of the yarn, then we are reducing the impact of the product itself. So 3 ways that we think are the way forward is reduce the amount of yarn used, use more recycled yarn in the composition, and somewhat invent a new yarn. On the screen what you can see is the yarn. So basically that is nylon, so it's man-made fiber that has been manufactured, and it then gets tufted in a non-woven technology into carpet, basically. So, you know, there's an important part of life cycle assessment and the impact of a product, and is as much as the raw material that makes it, but also its recyclability, and it's a true testament, and it's you know, sustainability has to be supported with the recyclability of a product. So we have developed in our factory in Holland, and we also have another similar project in the States. It's the re-entry recycling plant, which you can see a shot of. And basically this is a plant that takes post-consumer and post-industrial carpets, tiles, and separates the face yarn from the rest of the body of the carpet tile. It's very difficult to do so because we work in a heavy contract business. We work in we make carpets that are made to last, and they're made to be installed in offices where we have heavy footfall. So we make them very solid indeed, and so to take them apart is very difficult. So we are developing this technology. We're way in an advanced stage, and it's working, and it is a challenge, but it's one that we're loving to take. So once you have recycled and you've extracted your high energy intensive yarn from your carpet, what you can do is you can in theory recycle it, and the best thing you could do with it is to recycle it and close the loop and recycle it back into carpet yarn. Although it's very difficult because although it's a thermoplastic nylon, you cannot really melt it down and make it back into yarn. It just doesn't work like that. Spinning yarn and making yarn is a very difficult engineering feat, and to really recycle 100% something like nylon 6, you need to go via a chemical route. And so the Eckersley yarn, which we buy from our supplier, does just that. They have a plant in Slovenia, Aquafil, it's an Italian company. They have a plant in Slovenia where they take post-consumer nylon and nylon 6, and they basically do via the chemical route, and they recycle the nylon back into the nylon. So it's very broadly explained what they did. I call it the depot-repo process. Perhaps it's a bit of a complicated for someone that is not in the field, but basically you take your waste and then you cook it, and then you go back to the monomer, so the original soup. So you find yourself with a starting material that is as good as virgin material. So you can spin 100% if you go through the mechanical, through the chemical route rather than the mechanical route. You can recycle yarn via the mechanical route, but you can only put about 15% of waste, and you still have to use 85% of virgin material. And you know, we want to cut our link to the petrochemical industry. So we would like to recycle our products. Now, this leads me to a project that we're running quite successfully, and it's about social sustainability. The post-consumer nylon that a company like Aquafil and the Eckersley product use. So what they do, they go around the world and buy used nets because they are made of nylon 6, and they take these nets globally and they put them through their Eckersley process. So what we as Interface decided to do is to partner up with a couple of NGOs, non-government organizations, and go in places like Danahong Bank in the Philippines, where nets have no value once they're used, and so fishermen they just discard nets and they throw them in the water, they throw them off, and they end up in the mangroves, which are fish nurseries, and it's truly an ecological problem. So these nets usually are no interest to a big company like Aquafil, say, because they're very difficult to retrieve. So what we decided to do is to get an extra income for fisherfolk in the Philippines, and to get them to have extra income by collecting nets, which are laying absolutely everywhere in the Philippines. This is part of the project. You see, this is close to a beach in the Nahon Bank in the Philippines. This is before, and this is after our people went and cleaned up the place. We're working with NGOs so that the money from the recovery of the nets goes to the fisherfolk. There is no middleman. We want the money to go to the communities. This is why this is a socially responsible and socially sustainable project, and also it's good for the environment, clearly. We make up that about a kilo of nets recycled will provide about half a kilo of rice to a family. So that is a great project that has been going on for a year, and we're pushing in partnership also with Aquafil to make it become an even larger reality. Another, just moving away from social sustainability, another innovative and sustainable material that we have developed, and we were pioneers, is this bio-based yarn. We launched in September, I believe, a product called Photosphere. You can see our carpet tiles are the blue bit at the bottom of the arena there. And we were the first in the industry to use nylon, which is part bio-based. What do you mean by that is that about 63% of the mass of the yarn is extracted from castor bean. And castor bean is grown mostly in India and in China. The castor bean is grown in land that is unsuitable for other uses, so it's not a complete crop for food crops. And actually it helps stabilize the soil and fight erosion. So you can make nylon, in this case nylon 610, partially out of castor oil. So that is the chemical route on how to get the sebacic acid, which is the 10 components in the 610 molecule. And in essence, this is a very good start if we are to indeed cut our link to the oil well. So we were the first one to do this. Obviously, we would love to see 100% bio-based yarn, if possible, in the future. There's always something to bear in mind when you go and you look at bio-based materials. There's always an additional cost, and there is a restricted availability. So this is something that is a bit of a problem with bio-based or biopolymers. So in essence, that was just an extract of what we're doing. There is much more, but I thought this was the most pertinent for the day. So thanks for your attention.
Thanks, Luca. And moving on to Giammichele.
Hello, everybody. Thanks, first of all, for your invitation, which I've been very happy to accept. My presentation is actually a bit different from what we've seen before, because rather than talking of a specific material or not even a specific project, I would like to touch on our approach as designer. In my specific case, as engineer, the company I represent is an engineering design firm. So what I would like to touch on is more our approach rather than a specific project or a specific material. Obviously, I will use some projects as example because this is what we basically do. And the projects I've selected quite different in terms of scale, material, and also budget. So also quite different from a financial point of view. One of the projects is the Saudi Aramco Cultural Center, where the innovation, say, is not just about the material, but rather the way the material has been used, and in particular the material we've adopted for the facade. This image is one of the first image of, like, say, the architectural vision of the project, when it wasn't yet defined, completely defined, the material that was going to be selected for the facade. We've analyzed different options, and the solution which we came out with was somehow inspired by some of the references that the architects have proposed. And basically, the facade, the external facade, is made up of stainless steel tubes of about 80 millimeters diameter, external diameter, and which wrap around the entire building. This is obviously just the external envelope, so there's obviously a main facade behind that. And there's a transition zone. Basically, in the correspondence of the window, these tubes become flat in order to allow the light to come in. And so this is basically how this external envelope of tubes wraps around the facade, becoming flat in correspondence of the windows. Obviously, behind there's a proper facade, which is a sort of a traditional facade, apart from the shape of the buildings that you've seen in the previous render. So here the innovation is somehow the use of these tubes and the use of this material, which is typically a structural material rather than a typical facade material used for a facade. So the innovation was more in the use and in the aspects of the allowed to generate, which was also the architects were aiming for. The sustainability of the project, because this is not just about, this conversation is not just about the material research and innovation, but also somehow the relation with sustainability. In this specific case, is not strictly related to the facade system, as you can probably imagine, but it's more in the overall design. So I'm mentioning this because basically sustainability is actually a combination of different needs. So it's just not energy-wise. It's also, as Luca mentioned before, there's also other aspects which are not only energy-wise, but also social, but even economical, because at the end of the day, our clients have a specific budget, so there must be have a specific aim as well. Somehow we're talking of commercial buildings, so there must be also an economical sustainability, if you like. Another example is completely opposite to that, because it's not a high technological facade or system. Well, it is somehow technological, but the material is very basic. Is a natural material. This is a pavilion which has been designed and built for a few years ago, Design Week edition. So this is also one of the reasons why I like it to present it. And a pavilion is basically a dome, a bamboo dome. So a dome made of bamboo elements connected together via the steel elements are their nodes. In this case, the sustainability is pretty straightforward. No, it is in the material itself. The innovation, I believe, is in the way the material is used. So it is in the material, but it is also in the design, and it is also basically in the idea of proposing this natural material as a structural material. So this is part of a project that I've been developing with a Colombian architect, trying to take these natural material to proper structural material sort of use. And obviously the approach we follow both in the design from an architectural point of view, but also from a structural point of view, as we've analyzed the structure, is pretty much the same approach we followed in any other project. So it's a similar approach to a much bigger scale. So we've analyzed the mechanical characteristics of the material, we've analyzed the specific structures in terms of stress and deflection, and check that these were within certain limits. Obviously, there's no any international standard, but there's or not official say, but there's already some draft standards. So there was a bit of innovation even in our approach, trying to collect information from different researches done around. So I quite like the opposite of these two projects. Obviously, there are many examples. This is another one we currently a project we're currently doing in India, in Jaipur, where again the innovation is probably in the material, but also somehow also in the approach we follow, because the facade is in this case is comes out of generative geometry process, so a quite specialized sort of approach. The material is quite basic, because this element you can see here in the facade is basically ceramic element which are handmade in locally. So here again, now there's also a social sustainability aspect, if you like, which you also find very interesting. So every single element, because of the way it is manufactured, is slightly different one to the other. But then the way the different elements are put together allow to achieve what is a quite complex design, if you like. So just a couple of examples possibly that can allow to raise a discussion about this subject later on. Thank you.
Thanks, Giammichele. So, Gabi has been incredibly patient.
I'm the last one.
Please.
Thanks. Hello. Thanks for staying here with us. I'm the last one. I'm trying to move that. Okay, wrong. Which direction is that? There's nothing? Okay, here we go. Sorry. I'm Gabi Böhm. I'm working for Premier Composite Technologies in Dubai. Premier Composite Technologies is a manufacturer of advanced composite components. We started off around 25 years in South Germany, supplying already advanced materials to the boat building industry, aerospace, environmental and architectural industries. The company has been founded now in Dubai 2006, and we have just about 1,000 employees there manufacturing. The materials we are using are mainly glass and carbon fiber, depending on the structure requirements. We are using epoxy resins together with structural foam cores, and the outcome is basically a structural cladding element which we use for facade claddings, building envelopes, or roof elements. The advantages, I have to really read now. The components are basically built using glass, epoxy and prepreg skins partly in the structural core, as I just said. The glass reinforcements provide a sufficient stiffness to meet all the structural requirements. The E-glass epoxy laminate thermal expansion values are very close to steel. Therefore, usually the components fixed to steel substructures move basically parallel. The cores provide the suitable thermal and structural performance. We are using only continuous fibers, no chop strand mats, again due to structural reasons. The materials offer a lot of possibilities for complex shapes, which most of the architects like. I have to say most facades are not simple in geometry anymore. A lot of special finishes are possible. I come to this also a little bit later. We see a significant reduction in weight, which is very important. Usually a composite cladding has only 10 to 15% of the weight of an equivalent part built in concrete. Also the superior durability is a main factor. If the composite elements are protected against UV, they can last very, very long. Another very big advantage is the off-site fabrication, which becomes more and more important in construction projects. The clients don't want so much fabrication on-site. They prefer parts which come on-site finished, basically. We also see quite improved thermal properties, basically, as the structural cores, they contribute a lot to the overall properties of the cladding. I go there very quickly. Just a few values. If you use a normal 50 millimeter build-up composite panel, it has already a U value of 0.6. With additional insulation, usually rock wool or mineral wool, of 40 millimeters, you come down already to 0.35, which is very, very low. Still having a very light weight of this cladding. The weight, again, is very, very little. We reach around 20 to 30 kilos depending on the finish on the outside for structural composites. Usual panels in the size of 3 meters in width up to 12 meters in length. They span unsupported 3 meters. That means you don't need any additional structures. This means also quite a cost saving for the client. And in the meantime, a lot of research has been done also to reach very high fire properties. ASTM rating class 1 is no problem anymore, which it was a few years ago. We also have a very low shrinkage, which is very important when you look into structural building envelopes. The panels come out of the mold and they basically don't change anymore. They have very good resistance to water. Usually we reach a lifetime warranty of 25 years is no problem using advanced composites. Also repair works are a big advantage compared to GRC, for example. You can repair damages on site without removing or throwing the part away. I talk a little bit about the manufacturing process, which is quite important and uses actually most of the high-tech equipment. It starts off with the mold. Every composite element is molded, basically. Usually the molds are quite complex, biaxial curved. We are using 5- and 6-axis milling machines for very high accuracy and also to make sure that the design shape of the architect is fully taken one-to-one, basically. This is a mold which is 8 by 4 meters in size. The milling machine is 28 meters long, 8 meters wide, 3 meters high, basically the Z axis. This allows us to go for extremely large elements. We are actually limited by the transportation rather than fabrication. The cutting of the fibers are quite expensive. Is also CNC supported. That means you reduce the wastage of the materials. And again, this is a cost-saving factor. A few images about the lamination process. There's different ways. Wet lamination and then also more advanced lamination process like pre-preg lamination. Here is shown the demolding process. The part is extremely big, as you can see. The dark surface is basically the mold underneath. The part which is coming out shows already a very neat surface from the mold surface side, which doesn't need a lot of preparation basically for the finishes. This is a building envelope module, which is 8 by 4 meters. I showed the mold before. This comes out of the mold with the structural stiffeners on. This dark areas show the window areas where we later on insert the glass. Here the cutout is done already. Puzzle basically for the ceramic finish is done in the mold. It was quite complicated actually, as you can see here. The finish was it was actually a porcelain large size tile which was bonded on. Finishes are possible in many ways. Paint finishes, a lot of acrylic coats which have also a metallic appearance, tiles in any kind of variation, also metallic finishes like stainless steel, which you can see on the left side. Again, possible finishes. I come to a project which we did with UNStudio. It was the 2 454 in Abu Dhabi, unfortunately not built like this. We looked into the podium claddings at a stage where the design was quite advanced already, I believe. The idea was to create an innovative building envelope which comes on site in units which basically include already the windows, the insulation, the fixing grid for the interior fit out, and all these structural stiffeners. The module size was 3 by 13 meters, so we are talking of just under 40 square meters per cladding element. Extreme lightweight was one of the factors. Pre-assembly on site is possible to segments up to 100 square meters, depending on the hoisting capacity. The cladding is fixed directly to the RC structure, the concrete structure. There's no need for any steel substructure to hold. The cladding, we are just using adjustable fixing brackets basically. This again shows a significant reduction in installation duration and also a significant reduction in weight attached to the building. What we did in the early stage, we analyzed the modularity, which is quite important because we want to reduce the number of molds. The facade was very complex in geometry, very three-dimensional, so we found actually quite a suitable subdivision. At the end we were able to replace 21 GRC sub-elements with one GRP element, which reduces the joints, the danger of water ingress, and so on, really massively. To create the different shape or geometry around the window, because the design was not simple, we plan to work with inserts into the mold, so we can always use the same base mold basically. This shows quickly some vertical sections through the building, where the cladding is just bolted to the slabs basically. The insulation layer is also inserted, and it's basically a very simplified build-up. Quick structural concept. The movement joints basically are implemented parallel to the building movement joints. We work with normal load and dead load brackets, so you have no problems later on. The fixation is extremely simple. Again, we use a T bracket, we call it, which is adjustable in 3 directions to react on the larger tolerances on concrete. Again, the installation is extremely fast. We calculated basically to pre-assemble 2 to 3 panels on the ground within 2 hours, and then the pre-assembled segment again is fixed to the building in another 2 hours, very fast. I show a few images of the mold. We did a few samples because also the surface finish was quite tricky. Actually, UNStudio gave us quite some tasks there, which was nice. You can see the part coming out of the mold is already very accurate and defined. You see the complex shape there. And this was after the finish application. It was a mix between textured and smooth finish, which was actually quite attractive, as seen here. This is also an advantage with FRP, that you can create very different appearances on the surface, which you are not very, I think is very difficult with aluminium, for example, or concrete itself. The windows were basically frameless, which was also a very nice detail there. They are fixed with from the back side, were also removable. But the framing was gone, which gave a nice overall impression. Very briefly, one project we are currently building. It's a project designed by joint venture Buro, Happold and Foster. Very nice project, extremely suitable for advanced composites. I think there was quite an intense study before the design took place, which material would be the best suitable. Advanced composites were the winner at the end, which was quite nice. Again, important was that the finishes are applied before the parts come on site, high modularity and repetitiveness, very low overall U value in the building. We even, with additional rock wool, basically became lower now, down to 0.2. Integrated roof lights, which allow for a certain amount of daylight. Again, very large size modules, 10 by 3 meters, which are then pre-assembled to a segment which is 100 square meters in size. This is the steel structure. There is no secondary structure. The module size is 27 by 27 meters. And the largest free span for the roof cladding is 13.5 meters. This is the subdivision. We basically build 10 pieces per quarter of the module, which makes it 41 plus 41 panels for the whole roof module, which is 820 square meters in size. So they are really very, very big. This shows the assembly method. This shows the scale factor. And this is the first part now, which is pre-assembled. The green color of the cladding comes from the fire rating, from the fire-rated resins. The openings for the glass panels are there already. And this is basically the hoisting size. Missing is the finish, which we are currently actually applying. This is it. Thank you very much.
Thank you, Gabi. Everybody can take a deep breath now. I'll try to tie it all together as well. I mean, obviously this week and also the furniture all around us is talking about collaboration and different ways of working. And so I think what everyone presented, at least there's a piece of what everyone presented, which has to do with not only, of course, collaboration between ourselves or between your partners, but actual kind of collaboration between materials. And this is where the invention begins to happen. Whether it's what James is saying, that he's trying to get rid of the connections, although the connections are still what's necessary, or in the end, what Gabi is talking about, actually bringing multiple pieces together to make one, and so forth. So to push the discussion a little bit, I'd like to pass that around the table a bit, and if everyone could take a moment to speak about a relationship between a couple of materials that you use and how that pushes forward the inventiveness of what you're doing, be it maybe in a social nature or in a relationship between two very specific natures, specific materials. James, if you have 5 minutes, you can speak to that, and then you got to run catch a plane. Okay, so James first. Yeah.
I suppose part of engineering and architecture is all about exploring the relationship between the material and design. And in my particular case, having specifically started or having a particular interest in a particular material, glass, it's been about constantly trying to challenge what not only what design can allow us to do, which has been a lot to do with mechanics and the possibilities of software and design tools that we now have, but also once you get to that point, how you then challenge industry and fabrication to move out of their comfort zone into an area in which they can be persuaded to move with you. Now, in actual fact, the latter is often the harder part, because industry has, particularly in the glass industry, for example, it has a particular interest in modularization and producing as much of the same thing as possible. It's a commodity industry. So when we come to trying to push boundaries of design, you're often up against that glass ceiling, excuse the pun, but you're often up against that. So for me, it's about trying to engage industry to work with me on those ideas, be enthused by those ideas, and find ways in which we can get some of those ideas into projects, which then in turn can get other people excited about the ideas. And that's really what's happened, has been from the things we've done about making larger pieces of glass, which sounds kind of obvious, but it's not really, when so many other things were stopping that happening, to the point that when it's done, you sort of find that lots of people, lots of other, not only other people look at the demand and are interested in it, but also other fabricators that are in that line start to get interested in it, and then more machines get designed around it, and then more discussion happens around it, and then suddenly what was a unique situation becomes more the norm. So I suppose on every angle, on that specific material, that's been what I think the relationship between design and materiality becomes, and it's pretty applicable to most things and what most people are talking about today.
Yeah, thanks. Maybe, and Lucas, since you also spoke a bit more than anyone else about the kind of manufacturing process, maybe you can relate the collaboration that you have with the NGOs in Philippines and your industrial process, and how that's beginning to happen.
Okay. Yeah, that is a new thing for us, this project in the Philippines, and it has been quite challenging. But we are aware that with a global name and sustainability name, you do need to look at sustainability from every point of view. In the Philippines, it's very much removed from the industrial, manufacturing. But they do have a lot of discarded nets that we can use into our carpets. And these nets I think it takes about 500 years to decompose, and they generate ghost fishing that kills fishes and just without any really need for it, and the fishermen, they've just thrown away the nets, and something had to be done, and we felt that we had the opportunity to tackle this and to really explore in this social sustainability. So we decided to go for it, but it was challenging. It's a different culture, and it's difficult to get things done, and logistics has been a nightmare. But at the end, you see the picture before and after. The nets are there, and then they're no longer there, and then anybody can pick up some nets and take them to our NGO, and they will be immediately paid for the nets. Right. So you can imagine, when the fishing is not so good. Plus, we we have encouraged the communities to use this the SLA program, that is community banking, where it's like a group of 8-10 people put their money into a little box with free locks, and everybody, people that are struggling can borrow with very reasonable interests, and it works. It's in 80 countries. This system, we didn't invent it, we just joined the bandwagon. So it is making a difference. 130 families already, we figured, have been involved, and it's cleaning up the beaches, and it's giving value to a material that takes a lot of energy to make, and that's a problem. It is just the worst thing you can do with nylon is throw it away or burn it. It's a great thing you can recycle it. I hope he answers your question.
Sure. I would, and at the other end, Nuno, maybe can we pass it around the table once, and then.
Just to add another theme to your next intervention, because I think we also are quite advanced in time. Because you talked about the life cycle of the product, and I think it would be nice to hear from your sides, on your sides of your story, if that life cycle assessment is being done, and what are the results or the consequences for your production. And I think on your side, I would like also to do, maybe on the next one, just a question about how much this, besides the obvious benefit of cleaning up the beaches, how much does it cost then to recycle 100% of the nylon in comparison to use the raw material that you are using? But maybe first we.
I'll pass on the mic. Yes, I mean it's a great point. The economics of the whole process, and the supplier of the yarn made their calculations, and so the comparison in price between the recycled versus the virgin is very similar. So it's not that it's more expensive. And we live by the LCA. We actually came up with also something that is more comprehensive. That's called an EPD, Environmental Product Declaration, that not only looks into the CO2 emissions, but also at the other sides of the whole story of a product. And so are competitors. So the more sustainable the product, the better it is in the marketplace. And it's a great story, at least in the carpet industry, or the section of the part of the carpet industry where we work, where sustainability does give you advantage, competitive advantage. This is probably not always the case in other industries, but we're seeing it as being our leading factor. So
Michele, perhaps in architecture, the word research is engaging with a new understanding, and we kind of try to create new economical models for that. Related to your PV research, could you also expand on how do you actually make that happen? How does that part of the research tackles the company, and how does it? How can you make it function?
Yeah. Excuse me. Just the economics of the life cycle. I mean,
yeah,
all the global economics. Oh,
yeah.
Okay. Both of the project presented by myself, and I think 90% of the research project in Permasteelisa moved to the optimization of the energy balance. It means move straight to the balance, economic balance. I mean, The idea of the OPV, organic photovoltaic, is introduce something that in the building we need, the glass, the semi-transparent glass, that is also active. Active means that produce itself energy. So obviously is a bit add cost, add a technology in the glass. But if you look at the entire balance, at least you produce energy. So both for the life cycle, but also economics, you add something that at the beginning costs, but in few years it for sure move to save some money economics, or at least it is the direction. As I told you, I talk about just two projects, and probably the organic photovoltaic is it could be applied on building. The first application could be in some not building like the curtain walling, but could be something for just charge, cars, we hope in the future, or bicycle or whatever in the center of the city. At the beginning it is small, and in a few years we will move to building, but we want to add something at the building that try to go in the zero energy building. Okay.
Yeah, thank you, Michele. And this is, how large is the consortium that you're working with for the PV project? It's a large team of
it's
companies,
it's about 25 researchers,
okay.
based some of them in Rome, some of them in Turin and Ferrara, and in Turin and Ferrara University, they try to develop new molecular, new material that perform a bit better. And in Tor Vergata University in Rome, the research is more for the product. I mean, scaling up. We have a pilot line that can produce at the moment panels 1.5 meters by 1.6. So we are still testing it, but we are going to the certification, and we are probably ready for industrialization. But
we'll look out for it.
Yeah. I hope you will be the first, together with us, applying this new product. I hope so.
Yeah, that's true. Gabi, I mean, we worked with you specifically on the project in Abu Dhabi, and I think one of the things that we ended up speaking about, and you touched on a bit in your presentation, is about efficiency. So we talk about attainability, that something needs to be accomplished. And I wonder if you could touch on what you do in your process from the initial reception of our models, perhaps, until the end, that improves the efficiency of the process in the building itself.
I think it's very important to work from beginning with the architects very closely to optimize the modularity. The mold is a very labor and work intense part which you throw away at the end. Is not a very sustainable part, so you want to minimize it. It's also very expensive for the client, so you want to minimize the cost. So you try to look into optimizing the split, the modularity, so you reduce the number of molds, and therefore you make sure you don't your project becomes more sustainable in this kind. Also, I think it's very important to look into the full application of the materials from the structural point of view. Many clients, they say, oh, you need to put a steel structure underneath. I don't think you can do it without. You have to use the materials with all capabilities. They're extremely strong. They can be engineered, custom engineered, that you basically reinforce them locally on some areas where you need more loads to be taken. And then you eliminate a lot of substructure in steel mainly, which again contributes to the overall sustainability of a project. Also, I think the reduced installation time and also basically the off-site fabrication has actually quite some positive effects towards sustainability. We are currently looking, because composites usually have a very negative sort of taste. People say, oh, that's plastic, this is not good. But I believe the manufacturing process is actually quite neat. You don't use water or heat. It's mainly a hand application. Of course, the resin systems are oil-based. You use glass. But the durability is extremely high. You can, as our oldest project is 25 years old, and we never had to go back to do anything there. The structure works, everything works, and this is a project where the dome basically moves every day. It's a sliding dome. It is open and closed every day, so it goes through a massive stress and vibration every day. But the structure is fully intact. We never had to go back. I think advanced composites, how we call them, using epoxy resins and woven glass fiber, they actually have extreme durability. I would say really up to 100 years is no problem.
Okay, thanks. And to try to get all the way around the table, Micol will get to you as well. But Giammichele, you said at one point, behind is a proper facade. Is what you said about the project in Saudi Arabia. Yeah. And I wonder if you can, which means something that we all know as the facade that we probably have drawn or designed before, right? And I wonder if you can maybe talk about the relationship of that proper facade and then the improper facade that's on the outside, and where it's going, and how one leads to the next, basically.
Yeah, well, basically what I meant is what I mainly focus on the external envelope, now made of these stainless steel tubes, which is mainly in that specific case not a facade element, if you like, in a traditional meaning, but is more an architectural feature. Obviously, it has some functions as well. Maybe next step for us as designer can be also investigate whether, well, that function is obviously an aesthetic function. It's got some sort of solar shading functions as well, because it reduces size when the tubes pass in front of the windows, but it still presents some solar shading functions as well. So it will be also interesting for us as a following step whether we can use those tubes for other functions, for secondary functions. But that is not the main facade. No. So when I mentioned that there's a proper facade behind, I was actually meaning that yes, there's a sort of traditional facade behind. I didn't mean to seem reductive, in what I was saying, and even the fact that it's just a sort of an architectural feature, it's got an aesthetic meaning mainly, doesn't mean that the project, as I possibly mentioned, doesn't mean that the project is not a sustainable project, or that the project can get rid of that part of that component, which is obviously an essential component of the project. And the multi-functional, the different size of each component, I think is interesting. We talk a lot about material. Obviously, material is not for us as designer, at least a starting point, but it's something which we'll arrive to following the analysis of different options. And also something which has been mentioned, which I think is extremely important, is the process and the interaction among the different people, different figures involved in the process. So back to what Nuno was mentioning before, the life cycle cost is something which is extremely important, and it is something which, for us as designers, imply a very close interaction with the manufacturers. But it's not. This is only one side of the cost issue or cost aspects, if you like. For major part of the project or the building, we designed the post-occupancy evaluation is also another important component, is another important aspect. So that the design is actually is not a linear process, but it's more like a cycle process. So we also inform our own design from previous examples, and sometimes also from current example, no? And when we have the chance to analyze the project as it develops.
Yeah. And that the steel tubes may become the proper facade eventually.
Yeah, exactly.
Micol, something that picks up from what you were talking about is the idea that realizing some of these materials takes collaborations, but also that some of the materials are in themselves collaborations. Let's say, for instance, the acoustic panels, which were, let's say, the acoustic insertion of the wooden flexible panels. And I wonder if you could sort of talk about two things. First of all, how some collaborations may have led to the creation of these materials, if there is a kind of a material scientist and a designer involved, for instance, and then how the collaboration or the material system within those products begins to function.
It always depends on the company, on the material, and eventually on the designers. In fact, in our materials database, we currently have around 6,000 different materials and technologies. Few of them have been developed by single materials or / technology developers without really having a company behind them. So that means then that if you're interested in that product or in that technology, they will be licensed it to you. But then you should find some. If you're not a manufacturer yourself, then you should find some manufacturing facility. But these are like quite few examples. So that is rather a rare way of proceeding with material development. So in many cases, companies have research R&D departments or research and development departments internally, and there eventually they decide to collaborate with designers. And not in many cases, when you see how maybe you are able to use materials and what sort of options they offer. Sometimes you are positively surprised by the open-mindedness that you can read from the product data sheet, which means that during development a lot of working with the designers has been done, which means that you can tell that a lot of forward thinking has been done so that the material has not been just put on the market for a number of options, which maybe have some limitations. There will be some limitations somewhere, obviously, yes. But for some projects, yes, you can tell that the product has indeed been a whole project of development. So, but that is always depending on the company and. Yes.
Thank you, Filippo. Okay. Well, thank you all very much for your patience and all of your information, knowledge, and collaboration. And we hope to keep working with you. And yeah, hang around a bit, and we'll have some more conversations. So, thanks a lot, y'all.